24 steel blades come down into a single pine log at once, driven by steam, and every one of them has to enter the wood in the same instant. The gang saw that did it was built by the Wickes brothers of East Saginaw, Michigan. It could take a white pine log 3 feet across and lay down a stack of finished boards in one pass through the frame. Every board thickness was decided before the log arrived, set into the spacing between the blades, and nothing could be changed once the cut began. Men stood around it the whole time it worked. They set the iron dogs that clamped the log to a carriage running on rails directly beneath the swinging sash. They fed it, oiled it, and kept the belts and line shafting running. At the larger mills they did that for 12 hours at a stretch, 6 days a week, and some mills never shut down at all. The moment that brought a man closest to it was the moment it stopped. A log wedged or a blade bound in its own cut, and somebody walked in to find out why while the rest of the plant kept turning. 24 blades gave a mill enormous production. They also gave it 24 separate things that could go dull, bind, wander out of line, or crack inside a log. By 1887, more than 300 Wickes gang mills were running across North America and overseas. Keeping one of them cutting took 2 steam engines built inside the machine's own frame, a filer who could never fall behind, and a forest that had to keep arriving 1 log at a time. If you enjoy these documentaries, then subscribe. Thank you. Now back to the gritty history. Before there was a Wickes gang saw, there was a log, and a mill owner losing money for every hour it sat unsawn. A felled white pine did not become lumber by being touched once. It had to be squared, then ripped along its length into boards of usable thickness, and each of those boards had to come off clean enough to sell. In the early 19th century, that ripping was done a board at a time. 2 men worked a pit saw first, one above the log and one below in a dug pit. Later, a single reciprocating blade, hung in a wooden sash, did the same work, powered first by a water wheel and then, from the 1860s on, by a steam engine. Circular saws entered the mills around 1860 and cut faster than a single sash blade. A circular blade can only cut as deep as its radius allows, though, so log diameter capped the machine. The blade itself ran thick, up to ½ an inch of steel, which meant a wide kerf, and a large fraction of every log turned straight into sawdust before it ever became a board. Millwrights tried doubling the circular blades in the 1870s to reach deeper into a log, but the basic waste of a thick blade remained. Speed brought its own quality problem as well. Early circular saws, run at the pace mills wanted, tended to run out of true, and mill accounts from the period describe the boards that came off them as resembling washboards more than finished lumber. Every one of these methods, pit saw, single sash blade, or circular saw, cut 1 board, or at best a narrow slice of a log, per pass. None of them turned 1 log into many boards in a single motion. A mill trying to keep pace with a growing market had no way to multiply that output except by adding more machines and more men to run them. Henry D. Wickes and his brother Edward N. Wickes had been building mill machinery in Michigan since 1855, when they founded the Genesee Iron Works in Flint. By 1860, the operation had moved east to East Saginaw. In the middle of the pine country the mills existed to consume. The brothers, later joined by Harry T. and William J. Wickes, ran it as a family partnership. Through the years, the Saginaw Valley became one of the busiest lumbering districts in the country. Henry Wickes is credited with the original gang saw design to come out of the shop. A steam-powered mill saw built to rip 2 or 3 logs into boards at the same time rather than 1 board at a time from 1 log. Instead of a single blade in the sash, the frame carried a bank of parallel blades, spaced to the thickness of the boards the mill wanted. 1 pass of the carriage through the saw produced an entire log's worth of boards in the time a circular mill needed to produce one. That idea, a gang of blades working together, was not unique to Wickes. What made the Wickes machine worth 300 sales by 1887 was a redesign the shop carried out in 1869, 3 changes bundled into one machine. The sash was given an oscillating motion, so the parallel blades cut with even results across the whole bank instead of drifting out of line with each other. The stroke speed was increased, and the blades themselves were made from thinner gauge steel, cutting a narrower kerf and losing less of the log to waste with every stroke. None of the 3 improvements worked alone. A faster stroke on a badly aligned sash would only misalign the boards faster, and thinner blades under the same load that used to be carried by thicker steel needed a steadier, better controlled motion to keep them from wandering in the cut. The 1869 redesign was an argument that speed, accuracy, and thin blades all lived or died together. It turned the Wickes gang from a Saginaw curiosity into a standard piece of mill equipment, sold across the continent and exported abroad, a business that would go on to outlast the Michigan pine it was built to cut. By 1887, the works turning out these machines in East Saginaw had grown to match the demand for them. The machine shop alone measured 130 by 50 feet, with a 60 by 70 foot extension built onto it. It held 12 lathes large enough to turn shafts 28 feet long, a boring mill built around a 78-inch wheel, and 10 planers keeping pace with them. The foundry attached to the works ran what the company's own advertising called the largest cupola in the state, an iron melting furnace holding 8 tons at a single pour. A shop built at that scale was not incidental to the machine it produced. Casting and machining work of that size and precision was what let the Wickes brothers build a frame heavy enough to carry 24 blades and true enough to keep every one of them cutting to the same line, order after order, mill after mill. The line was sold under the company's own advertised name, the celebrated Wickes gang. What none of that solved yet was the mechanical problem underneath all 3 improvements. A saw blade hung loose in a frame and driven back and forth at higher speed does not become more accurate because a machinist wants it to. It becomes harder to control. The frame carrying 24 blades at once was heavier than the frame carrying 1. A heavier frame driven faster is a heavier mass to start, stop, and reverse, over and over, without ever letting the blades inside it drift out of their own straight lines. That was the problem the 1869 redesign created, even as it solved the problem of waste and speed, and it is the problem the Wickes brothers spent the next 3 years working out on paper before they took it to the patent office. A reciprocating saw blade only cuts on the way down. Gravity and the driven stroke put the teeth into the wood on the descent. On the ascent, if nothing changes, those same teeth drag back up through the cut already made, biting the wood from underneath, heating the steel, and tearing the grain instead of leaving it clean. Millwrights had known this since the earliest up-and-down saws, and they had a standard answer for it, called rake. The blade was hung leaning forward in its sash rather than straight up and down, so that as it rose, it tipped away from the wood instead of dragging through it. Oliver Evans, writing when these mills were still new, described exactly what the rake bought a sawyer. It gave the saw liberty to rise without cutting, and the log room to push forward as it rises. Rake solved the upstroke, but it created a timing problem instead. If the blade only cleared the wood at a fixed angle, the log could only be fed forward safely at that same fixed point in the stroke. The feed had to move in short ratchet bites, timed to the saw, rather than pushing the log through in one continuous motion. Every increase in stroke speed ran straight into that ceiling. A millwright could drive the crank faster, but the feed still had to wait its turn in the same rhythm, bite by bite, and a faster stroke driving the same interrupted feed bought very little extra lumber for the extra wear it put on the machine. The Wickes answer, patented in 1872, mechanized the whole idea of rake itself rather than building a better version of it, by making the entire sash move. Instead of a fixed lean built into how the blade hung, the whole frame carrying all 24 blades swung forward into the log on the downstroke and pulled back on the upstroke. That oscillating motion was driven by the machine itself, rather than set once by a millwright's eye. With the frame doing the work that a fixed rake used to do, the feed no longer needed to wait for a single safe instant in the stroke. It could run continuously, driven by its own mechanism, while the sash handled clearing the teeth on every cycle regardless of feed position. That is what let the 1869 redesign's faster stroke turn into faster lumber. It is why the patent Henry, Edward, and Charles Wickes, filed in 1872, granted that October 29 out of their shop in East Saginaw, mattered as much as the earlier improvements it made usable. The patent, numbered 302552, describes the specific engineering the Wickes brothers used to drive that oscillation. Existing oscillating frame designs, the patent noted, either failed to oscillate the sash at all or relied on true oscillating-type steam engines to do it, engines that were expensive to build and, in mill conditions, unreliable to keep running. The Wickes solution instead placed a pair of trunk engines low in the gang frame itself, connected directly to the lower girt of the saw sash by connecting rods. A trunk engine keeps its piston moving in a straight line even while the part it drives swings through an arc. That let the sash oscillate through its forward and back motion, while the engines inside the frame kept doing simple, reliable straight-line work rather than building the arc into the engine itself. Two engines meant two pistons that had to move together, so the design ran horizontal pipes between the ends of the two cylinders, equalizing steam pressure between them and keeping both pistons synchronized rather than fighting each other stroke for stroke. A separate friction wheel system controlled the speed of the feed rolls. Weighted levers fitted with adjusting screws raised and lowered the pressure rolls that gripped the log, working through bevel gears and discs to keep the log tracking straight as it moved through the saw. The equalizing pipe existed because two engines, built to identical drawings but never perfectly identical once cast, machined, and worn by use, would otherwise drift out of step with each other stroke by stroke. One piston would arrive at the end of its travel a fraction ahead of the other. In a frame meant to swing 24 blades in unison, a difference that small was enough to throw the whole sash out of true. Balancing pressure between the two cylinders kept that drift from accumulating over the course of a shift. It also meant the two engines now shared one system rather than running independently. A fault anywhere in it, a leaking gland, a worn valve, a partly closed cock, showed up as a problem in both engines at once, instead of staying isolated to one side of the frame. The mechanism carried its own trade-off, and the patent said so directly. The claimed advantage over a true oscillating engine was steadiness and stability rather than raw novelty, and the claimed advantage over a plain direct-acting engine was economy, not power. What the Wickes design bought was a frame that oscillated on demand, at speed, without the expense and fragility of an oscillating engine to drive it. What it cost was placing two steam engines inside the very structure that was supposed to be swinging 24 saw blades back and forth, a frame that shook by design now carrying the machinery that made it shake. That the oscillating sash was a genuine industry-wide problem, not a Wickes peculiarity, is confirmed by a separate patent filed 12 years later. In 1884, Theodore S. Wilkin of Milwaukee patented his own mechanism to give a gang saw sash an oscillatory forward movement during the descent and a corresponding backward movement during the ascent. Different shop, different mechanism, same problem, arrived at independently. Every gang saw manufacturer competing in the Great Lakes lumber trade in these years was solving the same problem. More blades and more speed meant a heavier moving frame, and a heavier moving frame meant more force required to start, stop, and reverse it in exact time, every single stroke, for as long as the mill wanted to keep running. No shop that built these machines escaped that problem. Inside the sash itself, the men who built and ran these machines had their own working vocabulary for the parts doing that work. The rod connecting the crank to the sash was called the pitman, a name carried over from the two-man pit saw crews these machines had replaced, one of whom worked in a pit dug beneath the log. The crank and a flywheel kept rotary motion smooth between power strokes, storing momentum to carry the mechanism through. A rag wheel drove the ratchet feed that moved the log carriage forward, and dogs, iron fittings with fangs built to bite into wood, held the log fast to that carriage so it could not shift or roll, while 24 blades worked through it. Each of those saw blades, meanwhile, was stretched taut under tension inside the rectangular sash frame rather than bolted into place, the way a bandsaw blade is tensioned. That tension let the steel hold a straight line through the cut, instead of wandering or buckling under load. A gang saw sash carrying 24 blades was, in effect, 24 separate pieces of tensioned steel, all required to hold that tension at once. All of them rode inside a frame that was itself being thrown forward and back by a pair of steam engines built into its lower girt. Every one of those 24 blades had to be right before the log ever arrived, not after. The spacing between blades in the sash set the thickness of every board the mill would cut from a given log, and that spacing was decided by the men running the mill, not by anything in the log itself. A sawyer, or head setter, chose the blade arrangement for a given run based on what boards the mill wanted to produce that day, locked the blades into that spacing, and only then sent the log through. Whatever the log turned out to be inside, whatever knots, rot, or curve it carried once the saw was already cutting, the blade spacing did not change mid-cut. 24 boards of a predetermined thickness came out the far side of the machine, whether the log deserved that treatment or not. Getting there took more than setting the spacing once. Each blade needed to be tensioned correctly inside the sash, tight enough to hold a straight line under load, and not so tight that the strain on thin, narrow steel became a liability of its own. The record does not give a single surviving figure for exactly how much tension a Wickes blade carried, what gauge of steel a given mill ran, how many strokes per minute the sash completed, or how fast the feed moved a log through the cut. What the mechanism tells us plainly enough is the shape of the daily work. 24 blades under tension, cutting at speed inside a swinging frame, needed constant attention to stay in that condition, and any one of them that fell out of it did not fail alone. A blade that went dull cut hot instead of clean, and heat in a thin, tensioned blade changes how the steel behaves under load, making it more likely to wander off its line. A blade that wandered did not produce one bad board alone. It threw off the spacing of its neighbors in the cut, because a log 24 blades wide has no slack in it for one saw to drift into the space meant for the boards on either side. A blade that overheated or lost its set could bind in the cut entirely. A bound blade inside a sash, still being driven forward and back by 2 steam engines, put strain on every other blade sharing that frame, on the girts holding them, and on the crank and connecting rods driving the whole assembly. Sharpening, setting, and tensioning 24 blades ran on continuously through the day rather than pausing between shifts, because that work determined whether the next shift could run at all. Sharpening a single saw blade was routine work in a mill running one saw at a time. Sharpening 24 and keeping every one of them at the same set and the same tooth profile as its neighbors on either side was a continuous task rather than an occasional one. A blade filed even slightly wider or narrower than the saws beside it would not cut the same board thickness the rest of the gang was cutting. That work had to be finished before the next log reached the carriage, and it could not be allowed to fall behind the pace the mill demanded of the sash. A saw run dull to save filing time only came back to the shop as wasted wood, a bound cut, or a blade that failed outright under load. This was the price the gang design paid for cutting 24 boards at once, and the price shows up clearest in what the same mills gave up when they ran a simpler saw instead. A moulay saw, an older single-blade design still common in smaller mills, carried one blade with no heavy gang frame around it. It needed less power to run, because the weight and friction of the heavy framework that held a gang saw's blades was, in a moulay, absent altogether. A single blade in a light frame has no other blades to stay in line with, no oscillating sash to be thrown forward and back by internal engines, and no 23 neighbors to disrupt if it drifted. The gang saw's whole structural burden, the pyramidal frame, the girts, the trunk engines built into the lower girt, the tensioning and truing of 24 blades at once, existed for one reason. It cut 24 boards from one log in the time a single blade cut one. Every pound of that frame, every one of its moving joints, was the cost of that multiplication, paid in mass that had to be accelerated, stopped, and reversed hundreds of times over the course of a single shift, without missing. A mule's single blade never had to answer for that mass. The gang's frame did, on every stroke, for as long as the mill kept feeding it logs. None of that machinery ran in isolation from the rest of the plant. A gang saw's steam cylinders needed steam, and that steam came from boilers fired, in most of these mills, by the mill's own waste. Sawdust and slabs, the very material the gang saw's thin blades were designed to produce less of, were burned to raise the pressure that drove the saw itself. The machine and its fuel supply fed each other in a loop that ran as long as logs kept coming in one end and lumber kept going out the other. Steam saws had displaced water power across the Michigan mills through the 1860s, trading a river's steady, limited push for a boiler's adjustable, more powerful, and considerably less forgiving supply of force. That supply lived under pressure inside a frame that was, by design, never still. Belts ran off overhead shafting to carry power to feed rolls and carriage mechanisms. Bearings along every shaft needed oiling through the shift to keep from running hot and seizing, and the whole chain from boiler to blade had to stay in adjustment at once. A gang saw idle for repair was a mill earning nothing while its fixed costs, wages, boiler fuel, and the standing capital of the machinery itself kept accruing regardless. Boiler explosions were a recognized hazard across 19th-century industry generally. One more form the same pressure took when it was not kept in check, though no surviving record ties a specific explosion to a Wickes-equipped mill. That risk sat under every gang saw running in the valley, load after load, whether or not it was ever recorded. Circular saw blades of the same period ran thick, as much as half an inch of steel, and every one of those cuts turned a proportional slice of the log straight into sawdust before it ever reached the boiler. The gang saw's thin blades were the whole reason mill owners tolerated the cost of keeping 24 of them tensioned and true at once, because more of the log came out as lumber and less of it came out as waste. But a blade thin enough to save that wood was, by the same fact of its thinness, a blade with less material in it to resist heat, and less stiffness to resist wandering under load. It also carried less margin before dullness or a bent tooth turned it from an asset into a hazard for the 23 blades running beside it. The saving in wood and the fragility that came with it were the same feature, looked at from two directions. Keeping that system running took a crew, not a single machinist tending one part. At a big gang mill, the work divided among specific roles. The head sawyer, sometimes called the setter, decided the blade spacing for a run and effectively controlled how the log would be cut before it reached the saw. Dogers, a title that described exactly what the job required, secured each log to the carriage with the iron dogs built to bite into the wood, making sure nothing shifted once the carriage began feeding the log into 24 moving blades. Carriage operators ran the mechanism that pushed the log forward at the rate the saw could take it. Relief men rotated through these positions over the course of a shift, because no single man held a physically demanding job like carriage operation or dogging for a full 12 hours without a break in the rotation. The rotation existed because the saw itself never took one. The carriage itself ran on rails directly beneath the swinging sash, so the men setting dogs and adjusting logs on it worked within reach of the same frame that carried 24 blades back and forth at speed. Resetting a dog, freeing a log that had shifted against it, or clearing debris off the carriage track put a man's hands closest to the machine at the exact moments the machine was already running. That work was done inches from a heavy structure that never fully stopped moving between logs. The shifts themselves were long by any modern measure. At the larger gang mills, one documented shift pattern ran from 7 in the morning to noon, stopped for an hour, and resumed from 1 in the afternoon until 6 in the evening, with a matching night shift running the same structure around a midnight break. More broadly, 12-hour shifts 6 days a week were standard at many mills, and some ran around the clock in continuous shifts. Through all of it, the men worked inside noise from the saw, the engines, and the shafting. Smoke hung from boilers fired on the mill's own waste. Sawdust hung suspended in the air around the saw itself, generated in quantity by every one of those 24 blades on every stroke. Mill hands earned between $30 and $50 a month, loggers somewhat less at $20 to $26, and in both cases the worker was expected to provide his own housing and his own meals out of that wage. In mill towns, the housing available to him was, by the accounts that survive, dingy and cramped. Accounts from Saginaw and elsewhere describe lost fingers, lost limbs, and lost lives in these mills, without the surviving record breaking those losses down into a specific count for gang saws as opposed to the rest of a mill's machinery. No casualty figure at all survives specifically for the historical Wickes gang saws that this documentary is about. That absence deserves to be said outright, rather than filled in with a number that was never recorded. What the record does preserve clearly is the mechanism of where the danger sat in a machine like this. Federal Workplace Safety Review of Gang Saw Hazards, compiled long after the Wickes era but describing the same class of machine, names the recurring points of contact. They are the moving blade, or the machinery around it, cranks and pitman rods and other moving components that require guarding, and feed-roll drive mechanisms that need to be enclosed rather than left open. They also include logs that can kick back and strike whoever is standing at the machine, and carriage cradles that have to be built high enough to keep a log from ejecting off the carriage during loading. Read against everything already described about a gang saw, the pattern makes sense on its own terms. The blades cut in a fixed, visible plane, doing exactly the job a sawyer could see and plan around. The drive underneath, the crank, the pitman rods, the rag wheel, the feed roll gearing, the sprockets carrying power from the shafting to the mechanism ran continuously and less visibly. It was there, at the machinery that moved the saw rather than the saw itself, that a moment of inattention turned dangerous. Every one of those categories mapped onto an ordinary task carried out on a working shift. Oiling a bearing running hot along the shafting, freeing a log that had kicked back against the carriage, clearing sawdust and offcuts that built up around the feed rolls while the drive underneath kept turning. Two documented incidents from modern sawmills, both at gang saws of the same general class and both far removed in time and place from a 19th-century Wickes mill, show that same pattern with a clarity the surviving 19th-century record does not offer. On May 5, 2016, at Hankins Lumber Company, a 53-year-old millwright was using a ratchet to adjust a malfunctioning positioning pin on the infeed table of a gang saw. His coat caught on an unguarded rotating sprocket nearby, and he was pulled into the mechanism. He died of broken ribs, a fractured sternum, and collapsed lungs. An unguarded rotating sprocket in the gang saw's drive caused his death. The saw blades played no part in it. On July 6, 1998, at a rural Iowa sawmill, a 22-year-old worker was clearing a plugged discharge duct on a wood chipper, a different machine, but the same underlying hazard. He was feeding a 28-foot steel cable into the running duct while the machine continued to operate. The cable caught in the chipper, wrapped around his neck, and threw him from the platform he was standing on, fracturing vertebrae in his neck and severing his spinal cord. The mill had no lockout procedure in place, and the chipper carried no emergency shutoff. Neither incident happened at a Wickes gang saw, and neither belongs to the 19th century. Both are cited here as documented, modern, clearly separate evidence that the specific hazard built into this class of machine has outlasted the machine's original century by a wide margin. It is a jam a worker tries to clear, or a fault a worker tries to adjust, while the drive is still live. The blades were the reason the machine existed. The drive underneath them, ordinary and largely unguarded by the standards later generations would demand, was where a working man was most exposed. That exposure sat inside a wage relationship the men had very little power to change. The same arithmetic that made an idle gang saw expensive to a mill owner, fixed costs paid regardless of whether the saw was cutting, made a raise expensive too. In 1885, that arithmetic reached the workers directly, rather than staying an owner's private calculation. Mill owners across the Saginaw Valley notified their workers that wages for the coming season would run 12 to 25% below what they had paid in 1884. On July 6, 1885, workers in Bay City struck in response, demanding a 10-hour workday in place of the longer shifts already described, higher wages, and pay delivered twice a month rather than however the mill preferred to schedule it. The strikers had a slogan for it, one that said exactly what the fight was about: 10 hours or no sawdust. 3 days later, on July 9th, strikers rallied at Madison Park and then traveled to Saginaw itself, closing mills there as they went. The strike turned sporadically violent, and local mayors requested both state militia and private detectives to restore order. Governor Russell A. Alger visited Bay City on July 19, an especially pointed visit given that Alger was himself a wealthy lumberman with a direct stake in the industry his militia might be called to police. 10 days later, on July 29, Terence V. Powderly, Grand Master of the Knights of Labor, arrived to support the strikers. Local labor voices like D.C. Blinn, editor of the Labor Vindicator and a Knights of Labor member himself, kept the demands in front of the public through the weeks of the walkout. On September 15, 1885, the Michigan legislature enacted a 10-hour workday into state law. By late September, though, the strike itself had ended in defeat. The hours were shortened, on paper, but wages stayed at the depressed rate the mill owners had set at the start of the season. The machine's appetite for logs had set the pace and the length of the shift that fed it. The men who worked that shift won a shorter day in statute and lost the argument about what they would be paid for it. The mills went back to running the same shifts on the same machines, feeding the same appetite for logs that had set the terms of the dispute in the first place. The scale of that appetite is what the production numbers from the years around it make plain. That appetite was not abstract. The largest gang-equipped mills, running at capacity, could saw around 100,000 feet of lumber in a single shift, a volume the older single-blade sash mills and even the early circular mills had no way to approach. A mill capable of that output had every reason to keep the 12-hour shifts running back-to-back. Every hour the gang saw stood idle for filing or adjustment was an hour of that 100,000 feet not cut, and every hour it ran was fixed costs, wages included, being paid off against production. Multiplied across an industry, that capacity added up fast. Michigan alone counted more than 1,600 sawmills by 1873, and Michigan lumber production as a whole climbed to its peak in 1889, at roughly 5.5 billion board feet in a single year. 1,600 mills meant 1,600 machines answering to the same fixed costs and the same pressure to keep cutting. In the Saginaw Valley specifically, the district where the Wickes brothers built their machines, annual mill output had already grown from a statewide value of about $1 million in 1840 to $6 million by 1860. The valley alone was generating some $7 million a year in mill product by 1869. Downstream, in the market these mills fed, Chicago's lumber receipts peaked in 1883 at more than 1 billion board feet passing through that one city in a single year, much of it cut on machines built to the same gang saw principle the Wickes brothers had refined. None of that volume could keep growing forever against a finite forest, and the industry's own numbers show exactly where the limit arrived. Michigan lumber production plateaued through the 1880s and then fell rapidly afterward, and by 1910, Michigan, the state that had led the nation in lumber production for the previous half-century, had become a net importer of the same commodity it once shipped everywhere. The white pine that built Saginaw's mills and the machines inside them had been cut faster than it could be replaced, and the industry did what it had always done when a region's timber ran out. It migrated from Maine to the Great Lakes decades earlier, and now from the Great Lakes onward to the Mississippi Valley, and then to the southern pine forests and the Douglas fir stands of the Pacific Northwest, chasing standing timber to wherever it still stood. A gang saw built to cut faster than any competing machine had, in the end, no answer to a forest that could not grow faster than the saw could cut it. Speed had been the whole point of the design, and speed was exactly what the remaining problem did not need. The gang saw's place in that migration ended for a reason distinct from speed. A different machine, arriving in the same decades, could see something the gang saw never could, and the difference came down to how each one decided what a cut would look like. Band saws, introduced and gradually adopted through the 1880s, cut with a thin, continuous steel belt of a blade rather than a bank of fixed saws in a rigid sash. That difference let a single band saw handle a log of nearly any diameter, unconstrained by the frame size that had always capped a gang. A band mill also put the decision about how to cut each log back in the hands of a sawyer working one log at a time, in real time, rather than locking that decision into a blade arrangement set before the log ever arrived. D. Clint Prescott, writing on the shift from gang mills to band mills, identified the exact cost the gang saw's own strength had been hiding all along. Gang saws, he wrote, produced a great deal of cullen stock from rough or unsound logs, because as the saws are hung in the sash, so must the lumber come out, and there is no way of varying the thicknesses to accommodate the quality of the stock. Every advantage of the gang, 24 boards cut identically and simultaneously from a blade arrangement fixed in advance, was also the reason it could not respond to a log that did not deserve that treatment. A band saw sawyer, watching one log pass at a time, could see a knot, a curve, or a soft patch of rot and cut around it, saving good wood that a gang saw would have sawn straight through and turned into waste, regardless. The kerf mattered too. Prescott put the comparison plainly. The saw kerf of a band saw is so much less than that of a circular saw that the saving in sawdust yielded a greater quantity of lumber from the logs. A narrower kerf, on top of the sawyer's ability to vary each cut, meant a band mill pulled more usable lumber out of the same log than a gang or circular mill running the same wood. When the North Wisconsin Lumber Company tested the comparison directly in 1893, 2 Prescott band mills cut 609 selected logs and produced 339,313 feet of lumber from them. That was a gain of roughly 30,000 feet over what the same logs would have yielded on a circular mill. Prescott was equally direct about the limit on the other side of that trade. Early band mills, he wrote, will not cut so much lumber in a day as a gang. A gang could outproduce a band mill in raw feet, cut per shift, for years after band saws entered the market. That advantage did not last forever. The gang's speed was spent turning marginal logs into marginal lumber, at a pace the market increasingly valued less than the band mill's slower, more selective yield of better boards from the same forest. The machine that could see what it was cutting beat the machine that could only cut faster, even while cutting less of it. Wickes Brothers itself did not disappear when Michigan's pine ran out from under its own home market. Export sales, already a meaningful part of the business by the 1880s, kept the firm running as its original Saginaw Valley customer base thinned out. The shop that had built its name on the celebrated Wickes gang diversified into the broader catalog of heavy mill machinery, lathes, boilers, and foundry work that it had always produced alongside the saws. A company built to arm one region's pine industry survived by selling the same engineering, trunk engines, oscillating frames, precision castings to whichever region still had standing timber left to cut. Around 1947, the firm merged with Wickes Boiler and U.S. Graphite to form the Wickes Corporation. By the middle of the 20th century, with patents still being filed under the Wickes name, Wickes Brothers had become one division inside that larger corporation, rather than the independent partnership Henry and Edward had founded in Flint in 1855. The consequence ran further than any one company's books. What the machine did to a log, the mill did to a valley, and the mills of the valley together, multiplied across the state, did to a forest that had looked, in 1855, too large to ever run out. What the industry left behind in Michigan was not disputed by anyone who wrote about it afterward. The pine forests that had made Michigan the country's leading lumber producer from 1860 to 1910 were, by the early years of the 20th century, mostly cut over, and the land left behind bred wildfires and erosion rather than a second growth of timber. It took a federal relief program, the Civilian Conservation Corps, planting tens of millions of trees through the 1930s, to put anything resembling a forest back on that land. A few decades earlier, the same ground had been feeding gang saws running 24 blades at a time, 100,000 feet a shift, in a state that could not, by 1910, grow enough lumber of its own to meet its own demand. What it took to run a Wickes gang saw was never only the 24 blades that gave the machine its name. It was 2 steam engines built into the frame those blades hung in, kept in exact synchrony by a pipe balancing pressure between them. It was every one of those blades held under tension, sharp, true, and correctly spaced before a log ever arrived, because a spacing set in advance could not be changed once the cut began. It was a crew rotating through shifts as long as 12 hours, feeding a machine whose fixed costs never paused, standing closest to the danger at the exact moments they reached in to fix something the drive had already started to fail at. And it was a forest that could supply logs faster than it could grow new ones, for exactly as long as it took a sawyer on a slower-sighted machine to prove that seeing each log mattered more than cutting it the fastest. The gang saw could put 24 blades through a log in a single pass. What it could never do was look at the log first. A machine that was slower and could look beat the machine that could not.